Let's dive into the world of virtual machines, exploring their implementation and how they manage resources. A virtual machine is essentially a software abstraction of physical hardware. It allows you to run multiple operating system environments on a single physical machine. Virtual machines provide isolation, enhanced security, and efficient resource management. There are primarily two types of virtual machines. Type 1, also known as bare metal hypervisors, run directly on the hardware. They do not require a host operating system, offering better performance and security. Examples include VMware ESXi, Microsoft Hyper-V, and Xen. Type 2 or hosted hypervisors run on top of a host operating system. They are easier to install and manage but typically offer lower performance compared to Type 1 hypervisors. Examples include VMware Workstation, VirtualBox, and Parallels. There are several key implementation approaches for virtual machines. These include full virtualization, paravirtualization, hardware-assisted virtualization, and binary translation. Here is a simplified example of how a virtual machine can be created. This is a basic virtual machine creation pseudocode. The function create virtual machine takes memory size and CPU cores as input. A new virtual machine is created. Memory is allocated using the allocate memory function. CPU cores are assigned using the assign CPU function. Virtual devices are created using the create virtual devices function. Finally, the virtual machine is returned. Full virtualization involves the complete simulation of the underlying hardware. The guest operating system runs unmodified and is generally unaware that it's running inside a virtual machine. This approach uses binary translation for privileged instructions, resulting in higher overhead but better isolation. In a full virtualization architecture, guest operating systems, such as Guest OS 1 and Guest OS 2, run their applications on a virtual hardware layer. The hypervisor or virtual machine monitor sits between the virtual hardware and the host's physical hardware, managing resources through binary translation and direct execution. Paravirtualization requires the guest operating system to be modified, making it aware of the virtualization. It uses hypercalls to communicate with the hypervisor, which leads to better performance than full virtualization. However, it necessitates a modified guest operating system kernel. Examples include Xen and KVM with paravirtualized drivers. In a paravirtualized environment, instead of executing privileged instructions directly, a hypercall is made. Prepare hypercall arguments, where the operation is hypercall memory allocation. Then, execute the hypercall to hypervisor and process the result from hypervisor. If the status is hypercall success, then return the memory address. Hardware-assisted virtualization leverages special instructions provided by the CPU to improve virtualization performance. This eliminates the need for binary translation, significantly improving performance. It supports unmodified guest operating systems and reduces hypervisor complexity. Intel VTX provides VMX root and non-root modes. AMDV provides SVM secure virtual machine. In a hardware-assisted architecture, guest operating systems run on a virtual hardware layer, similar to full virtualization. However, the hypervisor utilizes hardware virtualization extensions provided by the CPU, like Intel VTX or AMDV, to manage resources. The physical hardware includes a CPU with virtualization capabilities like VTX or AMDV, along with EPT/NPT and IOMMU. Effective memory management is crucial for virtual machines. Key techniques include shadow page tables, extended or nested page tables, memory ballooning, memory overcommitment, and page sharing and deduplication. Memory overcommitment involves allocating more memory to virtual machines than is physically available, relying on the fact that virtual machines rarely use all allocated memory simultaneously. In nested page tables or extended page tables, the guest virtual memory is translated through guest page tables to guest physical memory. These addresses are further translated using extended or nested page tables to host physical memory. This process is hardware-assisted, making address translation more efficient. This involves two translations: guest virtual address to guest physical address, GPA to host physical address. Efficient CPU scheduling is essential for managing virtual machine workloads. Techniques include mapping virtual CPUs to physical CPUs, time sharing between multiple virtual machines, implementing CPU caps and reservations, utilizing CPU pinning and NUMA awareness, and applying CPU overcommitment strategies. CPU overcommitment means allocating more virtual CPUs than physical cores available, based on the assumption that not all virtual machines will use their full CPU allocation simultaneously. In virtual CPU scheduling, the hypervisor CPU scheduler manages the virtual CPUs of different virtual machines and allocates them to physical CPUs. The physical CPUs execute the instructions from the virtual CPUs based on the scheduling algorithm. I/O virtualization presents several challenges, including device diversity and complexity, performance overhead, device sharing between virtual machines, interrupt handling, and the need for direct hardware access. Three common approaches to I/O virtualization are emulation, paravirtualized I/O, and direct device assignment. Emulation involves software emulating physical devices. The guest OS uses standard drivers. While offering high compatibility, it generally provides lower performance. Paravirtualized I/O uses modified guest drivers that communicate directly with the hypervisor, providing better performance than emulation, but requiring special drivers. Direct device assignment gives a virtual machine exclusive access to a physical device, offering near-native performance but limiting sharing and utilizing IOMMU or SRAOV technologies. To summarize, virtual machines offer hardware abstraction and isolation. Implementation approaches include full virtualization, paravirtualization, and hardware-assisted virtualization. Resource management is critical for performance. Memory management employs techniques like EPT and NPT. CPU scheduling balances virtual machine workloads. I/O virtualization remains a challenging area. Looking ahead, future trends include confidential computing with hardware-enforced virtual machine isolation, specialized hardware acceleration for virtualization, artificial intelligence-driven resource optimization and management, hybrid approaches combining virtual machines and containers, and serverless virtual machines with ultra-fast startup times. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.